And that's why I'm talking about RocksDB and how we put that on top of a zone SSD. And if you look into the agenda a bit, I'll start with a crash course into zone namespaces. I think there's a lot of new things, and the interface is different from the normal LBA interface. So let me also give you an introduction to that so everyone's on the same page. And then we're going to go into how we adapted RocksDB to work with the zone interface, what challenges we faced, and how we solved them, and then have a small demo and show how the drive operates under a RocksDB workload. And then we're going to discuss the results and see what we gain from this, and finish up what's next in the CNS ecosystem, what we're going to focus on after RocksDB. So, zone namespaces 101. Let me just give you, most of you probably have got an introduction, but before today, how many of you knew about zone block devices and zone namespaces? Okay, most of you. It wouldn't have looked like that a year ago. So, let me just fix this. Okay, okay. I'll just stand like this. Yeah, cables are the worst part of your system. Okay, zone block devices. What is this? Because this is the concept that the host stack is building upon. Well, it's a new paradigm in storage. Oh, this is good. Let me do it like this. Yeah, so zone block device is a new paradigm in storage. We split up the address space into zones, and each zone needs to be written to sequentially. And a zone must be reset before it can be rewritten. So you start writing to a zone by issuing a write at its start address. And as you issue writes, the write pointer moves until the zone is full, and then you need to do a reset to bring the zone back into a writable state. So the host manages and tells the drive when it's done with the data, and you can reuse the zone. And this fits a flash memory really well, because you need to do sequential writes on NAND. But this concept was not introduced for flash. It was done for SMR, single magnetic disk drives. And it was introduced as a technology to increase density in spinning Rust, but it shares the flash access model. You have to do erase before you rewrite, and you have to do sequential writes, and no in-place updates. But the underlying physical properties are quite different from flash. So single magnetic recording is a technology that sprung out of the fact that write heads need to be wider than the smallest readable track. So by shingling writes, just like shingles on your roof, you can pack more tracks into the same space. And this has been standardized, and it's out there already. Have Damien in the audience who's been talking about SMR longer than maybe he wishes to. But this is out there, and it's standardized in SAS through the zone block commands, and in SATA through the zone data commands. And it defines this model where the host and the drive can cooperate on the data placement to optimize the read, modify, write capabilities. So that's for SMR. What problem are we trying to solve here for flash? Well, today we have increasing amounts of data coming into our data centers. And the data centers are struggling with keeping up with this and scaling. And we get all these different unstructured data streams ending up on our drives. So we have databases, sensor workloads, analytics, virtualization environments, and video, all being dumped into our disks. And because the disks are forced to do sequential writes, it needs to serialize the data. And because all this data is unstructured, this is going to have to end up in the same erase blocks. And that forces this multiplex of data into the erase units, and that forces the drive in turn to do garbage collection. And garbage collection is bad because it increases write amplification, it increases over-provisioning needs, and thereby cost. So it both degrades performance and reduces your capacity. And also decreases throughput, latency, predictability, because the drive needs to do a lot of things in the background. And this is illustrated. Yeah? Okay, I'll move to this then. All right. Can you hear me now? Yeah, perfect. So, on the left here, we see a traditional or conventional SSD controller where data from all these different applications are getting serialized and mixed on the drive. While for on the right, we have a zone disk where the applications can place their data in separate zones and then avoid this mixing of data on the disk. And by separating data, we avoid the garbage collection case where where data from one application has to be moved out of a zone that is being freed due to another application being done with the data. And this eliminates the data streams multiplexing and decreases the write amplification and over-provisioning needs and increases throughput and latency predictability. So the applications can separate the data, but the application's internal data structures can also be separated. So you can do hot and cold data separation. So you place different types of data with different temperatures into different zones within the applications as well. And with this new interface, you need host software, right? But we don't want to reinvent the wheel here. We have a working ecosystem already for SMR, and we reuse the plumbing already done for zone block devices. So that'll make existing CBD-aware file system and device mappers just work once we've made the small additions and adaptations for CNS. And it will integrate with very well with SMR support in RocksDB, and Ceph, and FIO, and libcbd. Some of this is done already, like FIO, and the rest we're working on. And as I say, this is nothing new. It's already in production and available to the public. So we're aiming for a stack where both zoned SSDs and SMR drives can be utilized as part of the same abstraction model. And when we come to the specification, this is still a work in progress. It's an ongoing technical proposal in the NVMe working group. The architecture bits are all settled. The big things should all be done now. And we're moving to phase 3 any week now. Which means that mostly language things will be remaining, so the T's need to be crossed, the I's need to be dotted, and so on, but it's getting there. And zone namespaces will be exposed as a separate namespace type, and inherit the NVMe command set and add zone support on top of that. And it aligns with the existing host-managed models defined in SAC and CBC. but it doesn't map one-to-one. So you have to be aware of the details. Even if you've done and worked with SMR, there are some changes, differences that you need to be aware of. And there's some things added that includes this zone capacity that I talked about earlier today. And I will go in and do a recap on that. We have zone append, which is this new command that allows you to issue several outstanding writes and let the device tell you where they landed. That enables high queue depth. And we have something called zone descriptors. That's a type of metadata that you can attach to each zone to identify it, for example, for recovery purposes. So that's a multiple of 64 bytes. That could be anything you want to tag that zone with. And if we look a little bit deeper into the spec, the specification specifies that each zone is in a distinct state. So these states are empty, implicitly opened, explicitly open, closed, full, read-only, and offline. And these states change upon writes, so management commands and device resets. And the zone management commands are open zone, close zone, finish zone, and reset zone. So if you get a fresh drive, typically all zones would be in the empty state. So that's the initial state. And then would then transition into an implicitly open state if you just start writing to the first LBA in that zone. Or you could transition to explicitly open if you issue a open command. So the open command is a way of telling the device from the host that, hey, I'm going to start writing to this zone. Please allocate any resources you need for that zone. So typically, you would need to start some preparatory work to let the user write to the zone. And by issuing an open command, you will have a chance to do that in advance so you don't get a latency hit on the first write. And then the zone will transition to closed state for one of these states. Either if you tell it to close it and tell the device to free up any resources associated with that zone, or the device will do it itself if it runs out of resources and have to close the zone. And then it will go back to either implicitly open by just writing to it, or to explicitly opened if you send an open command in. And when you fill the zone, if you finished writing all this capacity, it will transition to full. And once you have reached the end of the lifetime for that data, you can send a reset command, and it will end up in the empty state. And if something goes wrong, this is undefined in the spec, but then the zone can end up in a read-only or an offline state. And one of the most difficult points to sort of absorb in the spec is the difference between zone size and zone capacity. So it's important to understand that zone size is fixed in CNS, and it's always an even number of 2. So it's 256 megabytes, 512. And the zone addresses will always be aligned on zone size. So it would always, the zone start addresses will always be a multiple of the zone size. But capacity can be less, because these zones align with the underlying media, and the underlying media might not have a capacity of an even number of 2. So the effective write range of a zone is the zone start address plus the zone capacity. So it's the writable area within the zone. So with this paradigm shift, there's a need to educate people and to give people access to all the resources that's out there. That's why Boston Digital has launched the Zone Storage Initiative and the site zonestorage.io. And this helps you get started with getting started guides, links to specifications. It documents all the support we have across the ecosystem in the open source world. And it's both for the developer community and for engineers in the data centers who want to learn how to make efficient use of both SMR drives and purpose-built zoned SSDs. So that's that. Let's look into how we've adapted RocksDB for CNS. So why RocksDB? Why did we pick this? Well, it's a very nice piece of the puzzle. It's a nice application to enable because it enables a whole lot of different things that uses this as a key value backend. And it's optimized for flash storage. It's written in C++ and optimized for things like flash. It's flash friendly because it's log structured, and it has customizable backends. And on top of this, an intern that has been working with us, Abutalib Tagaev, had already adapted RocksDB for SMR, so zoned block devices support we already have. So what remained for us to do is just to do the small bits that were needed to run RocksDB on top of our prototype development platform. So, but what problem are we trying to solve here? The RocksDB is already flash friendly, right? But we did measurements on the device write amplification, and we saw that it was significant. So we saw as the drive's capacity was filled up, it was forced to start doing garbage collection. And that soon leveled off to a factor of 4x. So that's a lot. Imagine having to do 3 extra writes per user write. So there was definitely room for improvement if we would start using CNS. So we had something to solve here. And why does this happen? I mean, we talk about flash friendliness, but we still have multiple streams going into the disk. We still had a mix of hot and cold data on the drive. So what we had was this sort of conventional, traditional deployment of RocksDB, where you have RocksDB itself trying to do smart data placement. We're doing this very well through LSM and sequential writes. And then you have a file system that it ships off its writes to, that itself tries to be smart in its block allocator and be flash friendly if you would be using a flash friendly file system like Btrfs. And then you have an FTL on the conventional drive that also tries to do its best in optimizing writes. But there's no guarantee that all these different parts will play together. And we saw the result, 4 times write amplification, right? So what we want is to use all the data placement knowledge or all the intelligence in RocksDB to do an end-to-end integration and do all the data placement from the application. But there were some challenges to be solved. We had multiple parallel files being written to. So we had these multiple streams, but we solved that by mapping each file to a set of zones. And we had to ensure that all writes would be sequential and ordered. And we solved this by making sure all the writes were sequential. That's an intrinsic property of RocksDB if you do correct configuration. And we have to ensure also that the ordering requirement, and that's not a guarantee in Linux unless you use DirectIO and the deadline scheduler. But by doing this, you get no reordering on the way. All sequential writes hit the drive. And we also have limited number of open zones on the drive, which means that we cannot keep an infinite number of files open, and we have to make sure that they're closed, all zones for a file are closed once we're done with the data, or done writing to that file. And we do that by finishing the zones when done with the write, so effectively padding them. And if we dig into the data structures of RocksDB and how we go from a key value insert into the disk writing, we start with the key value, and that is written through a write-ahead log into a mem table. And the write-ahead log ensures that until the mem table is flushed, we have a possibility of data loss. But the write-ahead log persists keys, so we can recover all the keys that have not made it into a mem table flush yet. And this is just a string of key values, and it's only used for recovery purposes, so it's easy to serialize this. It's not a performance hit if we need to do this during the recovery, because that's not on the critical path. So once the key value has hit a mem table and the mem table has reached a certain size, it will be flushed down into a sorted string table on the disk. And through compaction, several sorted string tables of lower levels will be compacted into higher levels sorted string tables. So you have a clear separation of hot data, so the low levels are hotter, and then they're compacted into increasingly colder files of the higher levels. And you have all this information in RocksDB about the data and temperatures and the different separation between different SSD tables, but this would be completely unknown to a conventional drive. It will just see this string of writes. But because we have this information and we're doing this end-to-end integration, we can simply separate all these files on the disk by mapping each file to a string of zones. So by separating files on zone level, we'll make sure that we don't overlap data between different files in different zones, and we don't have to evict any data or do any garbage collection once we're done with a file. It's really easy. So but we had this requirement on not having any large numbers or any finite number of open zones, so we have to do padding when a file does not align perfectly with zone size. So that induces a little bit of write amplification, but it's much smaller than the 4 times. It's just a small fraction of that. So to sum up the approach, we map files to zones. So we do zone management through file management. And zones are allocated when creating a new file, and zones are released after file deletion. And zones can be rewritten after being reset. And that means that we don't do any garbage collection within RocksDB. It does things copy on write, so there's no need to do that in the RocksDB. And we don't, because we have the zone interface and the host is managing the data placement, there's no on-device side garbage collection. So we effectively get a write amplification of 1 on the disk. And if we have a look at how this would be seen on how this would look in a demo, on the left here we see the console output of random inserts of key value pairs. And on the right, we have a tool that peeks into the disk and visualizes the zone states. So here you can see how zones are being written to. And once they're full, and the data has been invalidated, they're being reset. So you can actually see the inner workings of RocksDB managing end-to-end this disk. So you will see more and more data will come in. So more and more of this red area will be there. So it'll be redder and redder. But you'll also see this continuous flow of things filling up, then being compacted, being reused. So this is all possible because we have the way of peeking into the disk and seeing how it's being utilized. You don't get this in a normal drive. You can drill a hole into a zone drive, SMR drive, and see how the write heads are being moved. But yeah, here we just need a piece of open source software that shows this to you. So let's talk about the results. What did you gain from this exercise? Well, by doing smart data placement, we get close to 1x device write amplification in this use case. And that's compared to 3 to 6x, which we measured on conventional drives, depending on the exact workload. And that was done with a reference drive with 28% over provisioning. And by not doing any on-drive garbage collection, you can reclaim all that space needed to buffer the writes, or buffer the relocation. And that gets you a 20% increase in capacity compared to a conventional drive of 28% over provisioning. So that getting 20% extra, sort of for free, is awesome. So it reduces the total cost of ownership with 20%. But also you get this write throughput increase because the drive is not occupied doing garbage collection. And you get this side effects of a more predictable drive that will be more effective. Yeah.
Why is it only 20% if you increase the endurance significantly? Then it also translates to reduced TCO, right?
Yes. Yeah. Or you get better throughput. Depends. Yeah.
And also you eliminate the FTL from the drive, which can also translate to reduced cost.
Yeah. If you're using the drive to the death. No. This is done on our developer platform, so we don't do performance numbers on this. But if you, for the whole system's performance, you get a write throughput of 4 times X if you do 4 times less write amplification on the drive. Yeah.
What about wear level? It seems like you're writing to the same spot over and over and over and over.
But that's managed by the drive. So the drive does not, the spec does not say anything about wear leveling. So yeah, so the drive itself can allocate its erase unit, right?
Yes, and if the drive needs to do that, then there is some write amplification.
If it needs to relocation, yeah. But that is some. But we also have a feature in the spec called reset recommended. So the drive can go out and warn the host that, yeah, you should reset this. So it can do it at its convenience. Yeah. Yeah.
Does the rooms have same size, same numbers?
The same
Size.
The zones have all zones have to have the same size, but the capacity can vary. So there is space. The spec allows for different capacity in different zones.
I'm just wondering, a file in RocksDB, the size of file in RocksDB are different. So maybe one cell will be mapped to several ROMs
Yeah.
Okay, so who will be responsible for managing the mapping relationship?
Yeah, that would be RocksDB in this case. Yeah. So you have to keep a mapping of zones to, or files to zones in the application.
Okay, thank you.
Mm-hmm. Yeah.
In this test, what was the size of the SSD file? And did you fix the size of SSD across all levels? Or
I mean, once you start compacting, there's no guarantee what the end result will be. But we aim for an SSD. I think the first level was 512 megabytes, aligning with the zone size we were using.
And it gets larger, right?
And it gets larger, and typically is not aligned on 512. That's why we needed to do this padding.
So 512 megabytes zone size.
Yeah, that's what we used in this case. Yeah, but then this is something that is depending on your drive, right? Yeah.
And how, what's the performance of a single zone?
It also depends on the implementation of the drive. Either you can have the full throughput, or you can have a subset of it, depending on how many of the parallel units within the drive you assign to it. So it all depends on how you want to build your drive. Yeah.
What is the right size and the right alignment that you can use with this drive? When you're testing, you can write any size or?
Yeah, you can. I mean, depending on the block size of the drive, right? But we typically use, yes, RocksDB does large write, like 1 megabyte. I think it's the default. Yeah.
Except for the write-ahead log.
Ah, okay, right. So that's that we had to align on 4K. Yeah.
So why not support in the zone namespace interface support arbitrary appends?
Oh.
You know, we don't
Okay,
have
so
to
you would
do
buffer.
it
You would buffer.
with the SMR specification. You could make it truly, you know, a log segment.
Okay, a non-block aligned write.
Yeah.
Oh,
I just want to mention.
I like that idea, but it's crazy.
Be aligned to the sector size.
Why?
It's a block device.
But it's not a log device. It's a log segment device. So we just call it a zone block device. And we are making it a block device, but it does not have to be.
Yeah. Okay. Yeah.
Yes, but it's part of an ecosystem called block device.
Exactly. You know, it will. Yeah. Don't confuse people further here. It's fine. It's fine to pack several different inserts into it.
It's easy to manage it in a software layer.
Yeah.
Was wall enabled in this test?
Yes.
And you were coalescing for multiple?
Yeah. You have to combine the. You have to combine them into the minimal. Yeah. Yeah.
How is this any different than running RocksDB on top of F2FS? I mean, all you did was map the zones to files. You could have just put a zone managed file system underneath it, right?
Well, F2FS does not have the information about the different types of data. It doesn't. It can't separate hot from cold data.
Every SS table is a file, right? I mean, that's
Yeah, but it has no. It cannot know how long that data is gonna live. Hmm? Yeah. Yeah.
F2FS has zone block device support, and you may end up in a situation where your files are cleanly allocated, being aligned to zones, but that's not the general workflow of F2FS. So with RocksDB and the file size changing between table,
they don't change, they're immutable, right?
the size.
SS tables are immutable. That's the whole trick, right?
No, but F2FS doesn't know that it's RocksDB creating the files. It's not necessarily going to align the file start to a zone start and cleanly the zone.
Yeah, it has a block allocator, and you cannot assign, since the files abstraction is that a file can be of arbitrary size. So a file system would have to have the capability of packing several files into the same.
I think
Same song.
F2FS can use CNS, but then it's redundant if you use CNS directly.
Yeah.
How many open zones do you need to have this working?
Well, it depends on the implementation. Our development platform had 128, but it depends on your drive.
So with 128,
Yeah.
Just to an idea.
Yeah. So that was plenty. I think we saw in our current implementation about 30 to 40 open zones at the same time. Okay, so let me move on. So what did we learn from this? Well, if you have something flash friendly already, it's easy to leverage that. So with CNS, you can enable applications to go from flash friendly to flash optimal by making sure that you're perfectly aligned with the underlying media. And this was not rocket science to do, since we had the zone ecosystem already available, and this has already been done for SMR. We have libraries, tools, and emulation, so it's easy to get started and easy to add the support missing for CNS.
Question. So if you coalesce some writes in a host DRAM before posting them to the drive, so doesn't it mean that you have a kind of write hole? So in case of power failure, so you have to lose some data, aren't you?
Yeah, I mean, you do compaction in memory, right? But you don't reset the zones until you have written that data somewhere else.
Okay, but you, even for write-ahead lock, you cannot write 4 kilobytes. You need to write some larger amount, isn't it?
Right. Yes. True. If you want it completely power fail, then you'll have to have.
So my point is that it's maybe not fully apples to apples comparison. So it's.
Yeah, but in that sense, I mean, you still need to align on sector size, right?
Mm-hmm.
So,
Okay.
yeah. So depending on you can collect several different inserts and complete them once you've filled up a sector. So there are solutions. Yeah. Yep.
So in your first bullet here, talking about flash friendly and flash optimal, you seem to have an implication that flash has a one-to-one mapping of contiguous logical block addresses to the physical flash media, which in most flash and FTLs is not the case. So I'm trying to figure out what you really mean about being flash optimal in terms of CNS enabling flash optimal.
Flash optimal. Okay. That's this knowledge about the race units, basically, the zones.
Okay,
that
but those would not have to be block address based. They could be based on some of the other techniques provided within NVMe, such as the directives of streams.
Well, streams are more limited, right? You have.
They're actually less limited. You don't have to have any logical block allocation related to them.
Yeah, well, you typically have to have a limited number of streams, right? And you have to do some global allocation of streams for the disk, right? For the disk to be able to separate it.
No different than zones.
So then you would have to build a stream allocating service on your drive. In this case, it's easier because you can just split the logical address space among the different applications, and the applications themselves do not have to worry about different types of streams, but just make sure that it writes the data into different chunks of the disk. So I would see it as an easier way of separating the data. But I mean, you can do something very similar with streams.
The problem with strings is they are ephemeral, they are stateless. And you don't reset the stream, you rewrite the stream. And that's what you can do with ZNS. That you cannot.
Yeah, that's true, yeah.
Except all of this, if all of this is done up at the host level, where the host knows what was put into a given zone,
Right.
which is how you rewrite the zone or you clear the zone, that same is a true based on the host wrote into a string, keeps track of that, and deletes the data all at the same time. getting the same effect you have here without firing your application to write everything in sequential logical block sequence.
The stream model doesn't fit well with the POSIX programming interface. So if you want to manage your drive through the kernel without using a user space driver, it's way better to use a logical block address space interface.
And we can see streams. We have SMR support all through. We don't have the stream support, so it would be much easier to adopt this through the stack. Yep.
How small can a block be? Can it be 16 bytes? Is there anything in the specification that prevents it?
A block cannot be less than 512.
Is that in the specification?
Yeah. In the NVMe specification, you cannot have a block that is less than 512, right?
Linux cannot either.
No.
No. You change the...
You change the specification. Have a 1-byte block. Yeah, I like crazy ideas.
It's not a crazy idea. If you think about how Google GFS works, and that's created this notion of chunk, you append to the chunk a variable size piece,
Yeah.
and it helps you use that as a write-ahead log, without having to pad it.
No, yeah.
So there's
1-byte zones are the best.
Sorry?
1-byte zones are the best. But
No, I'm not talking about byte zones. I'm talking about not having non-blocked zones, basically.
Okay. Yeah.
Think of the file system interface as opposed to the blocking interface.
Yeah.
Use an arbitrary number of bytes.
That's something to meditate on. Yeah.
Yeah, so it's out of scope for this presentation, but what if you did not have a flash-friendly payload? How does it reflect on your results?
Well, it's a cooperative model, right? And if you do completely random writes, you cannot do anything on the drive. So that's the end. You have to have smart data placement. But it doesn't matter if you're not flash friendly, you're not flash friendly. There's no automatic pill that will just fix this up. So there's, yeah. Yeah. Depending on your drive. So the drive could just remap that and let you continue. You can also end up with reduced capacity in that zone and having the zone make this, having the drive do a zone excursion, saying that you have to continue writing to somewhere else. There are options on how to handle that, but it's drive specific. The zone abstraction allows for different implementations. Yeah, I just want to finish up by looking into what's next. Well, obviously we want to upstream this support to RocksDB. So we want to make sure that this is a standalone implementation and it's easy to plug that environment under any in any use case you would like to deploy, like using MyRocks or any of the other use cases there is for RocksDB. So there is some work left to do this and make it pretty. And then, of course, do more CNS end-to-end integration. So databases like RocksDB that are LSM-based are very good targets. We have file system work ongoing for Btrfs and Ceph. And, of course, we want to make some block devices and CNS plug into the cloud infrastructure. So with that, I'd like to thank you. And thanks for all the questions. If you have some more, I think we have time for that.